This is lecture number 12 of the course Engineering Mechanics. In this lecture, we are going to start the topic kinetics or dynamics. In the very first class of this lecture, first class of this course, I defined kinetics. Let's remind ourselves of that definition. This is the definition what we had earlier. Study of the motion of a particle or a system of particles and the relationship of this motion with the system of forces acting on the particle or that system of particles. As far as kinetics, the kinetics of a single particle is concerned, Newton's second law gives us that relationship. Here, the particle of interest is F. I have an inertial reference frame I. API is the acceleration of this particle with respect to the frame I. Mass m is the mass of the particle, and F is the net external force acting on the particle. This is a vector relationship, and with the help of this vector relationship, one can find API provided the mass of the particle is known and the net external force acting on the particle is known. Once API is known, one can integrate this acceleration term with respect to time, and we can get VPI, which will be the velocity of the particle of interest, and one more integration with time will give us the displacement vector of the particle at any time. All of us are well aware of this procedure. We have solved such problems in the past. In this course, however, our focus will be on kinetics of a rigid body. we would like to know if we have a rigid body M and there are several forces acting on that, how the motion of this body M will be realized under the action of these forces or the force system that is acting on the rigid body. There must be an equation that would relate these external forces acting on the rigid body on one side and the kinematics of the rigid body on the other side. We will look at that relationship very soon. Before we reach to that stage, we need to make ourselves familiar with some definitions. So in the next 20 minutes or so, I am going to define some new quantities, and those new quantities will form the basis for us to finally write a relationship between these external forces acting on the rigid body and the consequent motion of the rigid body. The first definition of relevance here is that of the center of mass Cm of a rigid body. The center of mass of a rigid body is defined as a point C such that the position vector of that point measured from a reference point equals this quantity. So this is the rigid body of interest M, and I wish to know the center of mass. I am measuring the position vector of the center of mass, say from point O. So this is the position vector RCO. How do we get RCO? We get RCO by doing this calculation. Now in the denominator we have this integral dm, which is over the entire body. What is dm? Dm is a small chunk of mass located in the neighborhood of point P. So P is a material point on M. Dm is a small chunk of mass in the neighborhood of point P. Now here note that I am using the symbol M in two ways. Here when I write M, I mean the RBM, the rigid body M, and then I will also use the same symbol M to denote the total mass of RB M. And this total mass is going to be indeed the integral of dm over the whole body. I will not write this word body every time. I will put this integral, and that itself will imply that integration is over the entire RB. If we go to the denominator now, what I have is the position vector RPO, which is this vector on this diagram. This is RPO, and then you multiply it with the small chunk of mass existing in the neighborhood of P and complete this integral again over the whole body. That will give you the position vector of the center of mass. Indeed, the unit of the position vector is going to be meters, SI unit. This is the definition of the center of mass. It may happen sometimes that the center of mass of a body may not be a material point, on M. For example, if we consider a rigid body of this kind, where these slanted lines are representing all the material points of the body M, it may turn out that the position of the center of mass may be here somewhere. This may be the center of mass. In this case, we will say that C exists on the massless extension of body M. In the last class, I did talk about the concept of massless extension of any rigid body. It was in the context of instantaneous center of rotation. Whether C exists on the massless extension or on a material point of M, we will still use the symbol C belongs to M. When C belongs to M, mind you that the velocity of center of mass with respect to that body itself will always be 0, and acceleration of the center of mass with respect to the same body will always be 0. Wherever the body goes, the center of mass goes with it. Whether the body is rotating or it's translating, the center of mass will go with it, such that the distance between the center of mass of the RB and any other point remains unchanged at all times. So you choose any point P here. The center distance between the center of mass and that point P does not change with time. Does not change in time. similar sounding quantity associated with an RB is the centroid of the RB, centroid of rigid body M. We use the symbol C star to denote this centroid. This is also a point. It is a point, and that point will again be part of M, which means either C star is a material point or C star lies on the massless extension. Extension of M. What is the definition of C star? This is the definition of C star. The numerator, both in numerator and denominator, you see this infinitesimal quantity dV, which is volume of a small volume in the neighborhood of point P. A small volume which is part of the RB in the neighborhood of point P. If I draw a diagram again, this is point P. We are considering a small volume in the neighborhood of P. This is dV. Again, this position vector is RPO, and C star may be lying here, and the location of C star will be found in this manner. Mind you, the integral dV is nothing but the total volume occupied, total volume of the RB. So what is the difference between the center of mass and the centroid? Centroid is what I am showing. I have already written on this slide, and let's remind ourselves. Center of mass was this. Now dm, the mass, a small chunk of mass lying in the neighborhood of point P, can also be written as rho times dV, where rho is density of RB at point P. And this density may be changing from one point to another across the RB. That density may be spatially dependent on the RB. If I replace dm here with rho dV, I get this quantity. So in general, RCO, RC star O and RCO are different quantities in general. C star is not the same as, in general, RC star O is not the same as RCO. But in the case rho is constant, RC star O becomes equal to RCO. centroid becomes the same as the center of mass. And that is easy to see. If density is constant, it can be pulled out from this integral in the numerator. It can also be pulled out in the denominator. Density will cancel out and you will be left with an integral in the numerator as rpo dv, which is exactly what we have in the numerator of the definition rc star o, and in the denominator of rco we will be left with integral of dv, which indeed is the same quantity what we have in the denominator of rc star o. Thus c star and c will coincide. The centroid of the rb will coincide with the centroid of the center of mass of the rb. Now every rb, every rigid body that we can think of, is strictly speaking a three-dimensional body. It will have a finite volume. However, we can make some engineering approximations in certain cases and simplify the determination of the center of mass of a body. For example, consider a body, a rigid body, which is very thin in one direction. For example, consider a thin plate. This is a plate of arbitrary shape. Now this thickness, which I am trying to represent with these lines here, if that is very small, then we know that the center of mass will be confined within this thickness itself. The location of the center of mass will be confined within this thickness itself. It may be anywhere on this plane, but it will be confined within this thickness. For a body like this, having very small thickness in one direction, the center of mass of this kind of rigid body can be found by performing two area integrals. Mind you, in the definition of the center of mass for a general body, we had two volume integrals. This is a three-dimensional integration, right, over the entire body. But for a thin body, RCO can be computed as where P is a point on the RB, a typical point on the RB, and then around that point, in the neighborhood of that point, I consider an area dA. Of P, neighborhood of P. Sigma is the local area density. So its SI units will be kg per meter square. Whereas in the original definition, when I expressed the center of mass in terms of density, this quantity is kg per meter cube. The SI units are kg per meter cube. Here it becomes kg per meter square, and here these symbol is an area integral. Area integral. Yet another simple case is that of a rigid body RB which has very small cross section area, like a thin wire. Consider this thin wire. Its cross section area is very small. Let P be a typical point on that wire, length of wire, and then we can identify a small length of wire in the neighborhood of point P. Then the center of mass of this wire length can be found using a line integral or a couple of line integrals as I am writing here. RPO lambda dl integral lambda dl, where lambda is the density of the material per unit length, kg per meter. That's all. Mass of the wire per unit length of it. So RCO can be found in this manner. And that C in general may be located at some point here, either on the wire or off the wire. Either on C may be a material point or C may be on the massless extension of the wire. So for such bodies having small cross section area, computation of RCO can be done in a more simple manner by performing two line integrals. So here this symbol means line integral. Sometimes we come across a rigid body which can be visualized as a combination of some regular shaped rigid bodies. For example, let's look at this diagram. So I have a cuboid, say of its edge lengths being A, B and C. For such a cuboid of uniform density, if the cuboid is of uniform density, its center of mass will lie at its geometric center. Now, if it is not of uniform density, then center of mass may lie somewhere else. Let's say this is the point where the center of mass lies. I'll call this as C1. Now, this cuboid is only a part of the rigid body of interest. Now, that rigid body may have now here this C that I used, this is small c and it is representing the edge length. It is not to be confused with big C, which I use to denote the center of mass of a rigid body. Now suppose the rigid body of interest is of this shape. This is the entire rigid body. So it is comprised of, clearly the rigid body can be considered, can be visualized as a combination of two cuboids, right? Combination of two cuboids. One cuboid has dimension edge lengths as small a, small b and small c. The other cuboid has dimensions edge lengths being small c, small d and small e. Now this small cuboid, the second cuboid may have its center of mass at point C2. And we assume that C1 and C2 are known already. The centers of mass of the two constituent cuboids of the entire RB are already known. And now I am being asked to find the location of center of mass of the entire RB. Entire RB means this whole thing. Can we use the information about the known locations of C1 and C2 to find C of the entire RB? The answer is yes. It can actually be derived very easily that the location of the center of mass of this entire RB can be found in this way. This would be the center of, this is how you compute the location of C, where RC10 will be this vector. This is RC10 and then this is the vector RC20. We can generalize this expression for an RB which has n constituent parts of which you already know the locations of the centers of mass. The expression will be this, where Mi is the mass of the ith part of RB and Ci is center of mass of the ith part of RB. As I said, this can be proved. However, I am not showing the proof in this recording. Sometimes we come across an RB which has its material distributed over let me draw a more regular shape to illustrate this point. Let's consider a circular plate. Now this circular plate will have, if suppose its center of mass is known, suppose it is of uniform density, and then its center of mass will be at say C1, and this is, I am calling as part 1. And then due to some requirements, due to some specific requirements, it may be required, due to some expectations, it may be required to remove this part of the plate from the full circular plate. So this blue color now shows hollow, no material. Let me call this as part 2. So now we have an RB which is actually part 1 minus part 2. Part 1 is full circular plate, and part 2 is also a circular plate, but the small circular plate, right? So if you take the small circular plate out of the full circular plate I showed earlier, part 1, our RB of interest becomes, an RB of interest has the shape which is circular on the outer periphery, and then a part has been removed. Now the formula that I wrote earlier on this slide to find RCO of an RB which has n constituent parts, and we know the locations of the centers of mass of all those constituent parts, can be used to find the center of mass of this RB. We can still use the same formula. I equals 1 to n mi RCIO, and mind you, when I say this part has been removed, the removed part would have had its center of mass at C2, right? The removed part had its center of mass at C2. So this formula can be still we can still use this formula. However, we will have to make a simple adjustment that M2, which is the mass of the removed part, in this formula should be written as minus of, or rather I should say M2 should be negative of the mass of the removed part. Even though mass cannot be negative in the context of this course, but to leverage this formulation that I have shown here for a situation like this, what I have on the slide, if you set M2 to be negative of the actual mass removed, you will eventually get the right location of the center of mass of this RB, which has this small part removed from it. All right. With this, we are done with the definition of center of mass and also how to compute centers of mass, location of the center of mass of an RB with various constituent parts. The next definition I want to introduce here as we prepare ourselves to start the topic kinetics is the momentum of a rigid body with respect to frame F. Momentum, this quantity is a vector quantity and it is defined as where again this integral is over the entire RB of interest. P is a typical point on the RB. F is the reference frame in context, and dm is a small mass in the neighborhood of point P. This is how we define the momentum of the rigid body with respect to frame F. The SI units of this quantity, the momentum vector, will be kg meters per second. Based on this definition, we can show that the momentum of a rigid body can be expressed in terms of the velocity of the center of mass of the body with respect to frame F. And mind you, VPF here is the velocity vector of point P with respect to F. Now since momentum vector is VPF integral dm, we can write VPF as where O is a point fixed in the reference frame itself. The velocity of point P is indeed the time derivative of the vector RPO, which in this diagram will be this vector with respect to frame F. Now here in this expression we have a time derivative acting on RPO, and then we are integrating the whole expression. We can change the order of these two operations, the time derivative and the integration. I can pull out the time derivative operator, do this integration first, and then let the time derivative operator act on the resulting vector. The moment you do this change in the expression, we realize that what is inside this square bracket, square parenthesis, is basically total mass of the RB multiplied by the position vector of the center of mass of the body. Center of mass may be lying here in general. And since mass is not changing with time, this becomes rate of change of position vector of the center of mass, which by definition is velocity of the center of mass of the body with respect to F. Thus, the momentum of a rigid body with respect to frame F can be expressed directly in terms of the velocity of the center of mass with respect to the same frame and the mass of the body itself. So there is really no need to perform this integral every time to find the momentum of that RB. If we already know the total mass of the RB, then we only need to know what is the instantaneous velocity of one point of the RB, and that would be enough to find the momentum of the entire RB. But that point is a special point, and that special point is the center of mass of the body.